We have a large circle, and perfectly inscribed inside it is a scalene triangle, ABC. We are given all three side lengths of the triangle. The left side, AB, is 13 units. The bottom side, BC, is 14 units. And the right side, AC, is 15 units. Our mission is to find the exact radius of the circle. Let's start by drawing a vertical line from point A straight down to the base BC. This line meets the base at a right angle. Let's call its length H. That altitude splits the original triangle into two smaller right triangles. It also divides the base of 14 into two pieces. Let's call the left piece x. That means the right piece must be 14 minus x. Now we can apply the Pythagorean theorem to both right triangles. For the triangle on the left, h squared plus x squared equals 13 squared. Since 13 squared is 169, we get h squared equals 169 minus x squared. For the triangle on the right, h squared plus the quantity 14 minus x all squared equals 15 squared. Since 15 squared is 225, we get h squared equals 225 minus the quantity 14 minus x, all squared. Since both expressions equal h squared, they must equal each other. So we can write 169 minus x squared equals 225 minus the quantity 14 minus x, all squared. Let's expand the quantity 14 minus x, all squared. That becomes 196 minus 28x plus x squared. Substituting that in gives 169 minus x squared equals 225 minus 196 plus 28x minus x squared. Notice something beautiful. Negative x squared appears on both sides of the equation. Those terms cancel immediately. We're left with 169 equals 29 plus 28x. Subtract 29 from both sides. That gives 140 equals 28x. Now, divide both sides by 28, and we get x equals 5. Now let's find h. Substitute x equals 5 into our earlier equation. H squared equals 169 minus 5 squared. 5 squared is 25, and 169 minus 25 equals 144. So h squared equals 144. Taking the square root gives h equals 12. Great! We now know the altitude of the triangle is 12. But the puzzle is asking for the radius of the circle. And this is where the clever geometry begins. Draw a diameter starting at point A. Let it pass through the center of the circle O. Continue it all the way down until it touches the circle again at a new point M. Now connect point M to point C. Because AM is a diameter, there is a famous circle theorem that says any triangle that uses the full diameter as its hypotenuse is automatically a perfect right-angled triangle. So triangle ACM is a right triangle. Now compare triangle ACM with our original triangle ABC. Notice something remarkable. Angle B and angle M both intercept the same arc, namely arc AC. Another geometry rule tells us that if two angles point to the same arc, they are identical angles. Let's call both of them alpha. So, both triangles contain a right angle, and both contain the same angle alpha. That means the two triangles are similar. Since they are similar, corresponding side ratios must match. In the original triangle, the side opposite alpha is the altitude, which is 12, and the hypotenuse is 13. In the larger triangle, the side opposite alpha is AC, which is 15, and the hypotenuse is the diameter, AM. Let's call that diameter D. So we have 12 divided by 13 equals 15 divided by D. Cross multiply. 12 times D equals 13 times 15. 13 times 15 equals 195. So, 12D equals 195. Divide both sides by 12, and we get D equals 195 over 12. But that's the diameter. The radius is exactly half of the diameter. So the radius equals 195 over 12 divided by 2, which simplifies to 195 over 24 units. And as a decimal approximation, that's exactly 8.125 units. If you figured it out before the end, let me know in the comments, and I'll see you in the next one.